Hi everyone, let's understand how elbow comes from KL divergence and why maximizing elbow is helpful. In variational inference, we want to learn the true posterior, but it's hard to compute. So we approximate it with a simple distribution Q of z given x. And now we use KL divergence to measure how close our guess, which is Q of z given x, is to the real thing, which is P of z given x. So this KL divergence is always positive and becomes 0 when Q matches P. So here's the trick. We can't compute P of z given x directly, but we can rearrange the terms using the elbow, which is evidence lower bound. And since the P of x, log of P of x is fixed, if we make elbow bigger, then the KL divergence becomes smaller. That means we can say they both are inversely proportional to each other, and that means maximizing elbow is equivalent to minimizing KL divergence. So in short, elbow helps us to bring our approximation, which is Q of z given x, closer to the real P of z given x, which is our goal. Thank you. Hi everyone, let's break down the KL divergence between two multivariate Gaussians. Sounds scary, but stay with me. Imagine you have two blobs in space. Both have shapes in ellipses. These blobs represent two different multivariate Gaussian distributions. Now, KL divergence tells us how one blob differs from another, but not in just terms of center, but also in terms of shape and spread. That means covariance. So, formula involves comparing their means and their covariance matrices. So, means that how far the centers are, and the covariance tells us that the direction and the spread of the blobs. So the KL divergence will be 0 only when the Gaussians are exactly same. Otherwise, it gives a number that says here is how inefficient it is to assume that one distribution while the data actually follows the other. So in simple terms, we can say that the KL divergence is just a fancy way of measuring how different two probability clouds are in higher dimensions. So that's it. Thank you. Let's talk about why the KL divergence term in the elbow is so important, especially in training variational encoders that are VAEs. Think of KL as a regularizer. It keeps the learned distribution close to a known prior, like a standard normal distribution. Without this term, the model might learn a very weird or overly complex latent space just to reduce reconstruction loss. So what happens if we omit it? The model will memorize the training data very well, but won't generalize. The latent space becomes chaotic and loses structure. This means you can't sample new and meaningful data, which defeats the whole purpose of generative AI model. So in short, KL divergence acts like a leash. It gives freedom, but also keeps things in control. If we skip it, then of course the model will work good on training data, but it will fail in generation. Thank you. So let's talk about mode collapse in GANs, where the generator produces the same output for every few variations, no matter what input we given. So it's like a student memorizing one answer that always fools the teacher instead of learning the whole subject. So if a generator finds one output that fools the discriminator, it will keep generating that, ignoring the diversity of the real data. The gradient from the discriminator becomes uninformative, and the generator stops improving. So the solution for solving this problem can be like few of them, and few of them are like use Wasserstein GAN. It gives a meaningful gradient even when discriminator is strong. Add second one would be add mini batch discrimination to help the discriminator detect lack of diversity, or we can also use unrolled GANs, which let the generator peek at how the discriminator will react in the future steps. So mode collapse is both mathematical and training stability issue, and tackling it helps generator GN generate richer and more realistic data. Thank you. So let's talk about the posterior collapse in VAEs, which is variational autoencoders. This happens when an encoder stops using the input and instead outputs a distribution very close to a prior, like saying every input is the same. This leads to poor reconstructions and the meaningless latent space. Mathematically, this happens because the KL divergence term in the elbow loss forces the learned posterior to match the prior. If the decoder is too strong, it can reconstruct data without using Z, and the KL term collapses to 0. So basically, when there is over regularization, then there is underfitting, which also leads to posterior collapse. But there are ways to overcome it, like KL annealing, like start training with low weights on the KL term and gradually increase it. This lets the model first learn to use the latent space. or we can also use weak decoders, so the model is forced to use Z. In short, posterior collapse makes VAs very lazy, and these things keep the latent space meaningful.